Hello everyone, and welcome back. Today we're going to continue our exploration of ordinary differential equations and focus on a particular class of differential equations that are very important in theoretical aspects and also several basic applied models as well. In particular, the class of differential equations that we're going to study today are linear first-order ordinary differential equations. So no nonlinear terms, no higher order derivatives, no partial derivatives, nothing fancy, just linear first-order differential equations. In some sense, a very safe place to start. So one principle in terms of linear first-order ODEs is that it can always be represented in the form y prime plus ay is equal to b, where a and b are functions of x only, right? So obviously we're going to have two cases to study here. So case 1 and case 2. So case 1 is the case where bx is identically equal to the 0 function, and case 2 is the case where b of x is not equal to the 0 case. So when b of x is not equal to 0, then we're going to be referring to this differential equation as a homogeneous first order linear differential equation. And over here, this case 2, this is going to be our inhomogeneous first order linear ordinary differential equation. So let's start off with the easiest case first, the homogeneous case. So can we solve all homogeneous linear first order ordinary differential equations? Let's see if we can. So if that is the case, that means y prime plus axy is going to be equal to 0. So can we always find a solution? So the first thing I want to do is I want to write that y prime as dy over dx. So we're going to have dy over dx is going to be equal to minus a of x times y. And then I want to rearrange this equation a bit. So I can write that as dy divided by y is equal to minus ax dx. So what do we have here? Well, this equation should look familiar because that's precisely a separable ordinary differential equation. So that means all homogeneous linear first order ODEs are separable. And if you don't remember, all separable equations can be solved by basic integration methods. So we can integrate both sides of this equation. So on the left hand side we have the antiderivative of 1 over y, which is going to be the natural log of the absolute value of y, is equal to the negative integral, let's just write it as ax dx. Right? So let's just keep it like that, and we could say, okay, let's assume that the derivative of capital A is equal to little a, but I'm not going to go ahead and do that. Let's just keep it in that form. So we can actually say that this is the implicit solution, but we can actually solve for y in this case. So we see that y is going to be equal to e to the integral, negative integral, of ax dx. Right? So the solution of homogeneous linear first order ODEs is in some sense always some type of exponential function, which is actually pretty cool, unless that numerator, that exponential term is a logarithmic function, right? But in some sense it has the structure or the potential structure of an exponential function, which is actually pretty interesting. So since we have proven that we can always solve every homogeneous linear first order ODE, let's actually look at a particular example of one. So let's assume we have 7x squared times y prime plus xy is equal to 0. With the initial condition, y of 1 is equal to 5. So we're looking for a particular solution, not a general solution for this ODE. So the first requirement that we have for this ODE is that this linear term, this first term before the y prime, is not equal to 0, which means that x cannot be equal to 0. So we have a singularity on this domain, so we probably should be restricting x to be a positive number because our initial condition is greater than 0. Right, so that's going to delete any singularities that this differential equation may have, so we can divide both sides by 7x squared and not have any issues. So we're going to have y prime plus 7 over x y is equal to 0. right? And then we can start isolating this equation. So we can write this as dy over dx is equal to minus 7 over x y minus 7 over x times y. And then we can isolate, so we're going to have dy over y is equal to minus 7 1 over x dx, and then we can integrate, right? So once we have this, what do we have? So this is going to give us the natural log of the absolute value of y would be equal to minus 7 times the natural log of the absolute value of x plus some arbitrary constant c. Since we're taking x to be a positive number, this absolute value on the x is not necessary, but I'm just keeping it there just to be safe. We can actually get the explicit solution. We can exponentiate both sides of this equation. So we have that y is going to be equal to, and we can actually bring this minus 7 up to this x. So we're going to have e to the natural log of x to the power minus 7 times e to the power of c, and we're going to define e to the c to be equal to some other constant k, just to make things nice. That e and that natural log are going to cancel, so we have that y is equal to k times x to the minus 7. So that is our general solution, right? So keep in mind we had an initial condition that we needed to satisfy. Y of 1 must be equal to 5. So let's see if we can find that constant k to make that true. So 5 is going to be equal to k times 1 to the power of minus 7, which is just the same thing as k. So k must be equal to 5. So that means y must be equal to 5 over the 7th root of x, right? So that is our particular solution to our differential equation, right? So solving homogeneous linear first order ODEs is actually pretty easy because it's just a separable ODE. But now let's take a look at the slight complications that come for the inhomogeneous case. Before we get into the solution of inhomogeneous first-order linear differential equations, I just want to bring up a very basic rule from single-variable calculus. There's the product rule for derivatives. So let's assume that we're interested in finding the derivative of the product of two functions of x, f of x and y, which is assumed to be just a function of x only. So the product rule says that this is going to be equal to f times the derivative of y plus y times the derivative of f in any order, since it's addition, and of course multiplication is commutative as well. But as long as y prime is with f and f prime is with y, then that would be correct. Now you may be wondering, why would I introduce such an elementary thing when we're supposedly far beyond single variable calculus? So let's actually dive into the non-homogeneous differential equations that we want to focus on. And I actually just want to start with a basic example to sort of see where we can actually use this product rule for quickly solving these types of equations. So let's assume that we have x squared times y prime plus 2x times y is equal to cosine of x. So this is obviously a first order linear non-homogeneous differential equation. Therefore, we should be able to solve it. At least that's my claim. So do you see anything similar between the product rule and this inhomogeneous differential equation, in particular the left-hand side? You should, because notice that y prime is the derivative of y, and 2x is the derivative of x squared. So if we observe that the left-hand side is precisely the product rule, in particular the derivative of x squared times y, then what we've done is actually rewritten this inhomogeneous differential equation as a separable differential equation. In particular, on the left-hand side, we have the differential of x squared y. On the right-hand side, we have cosine of x dx, and we can integrate both sides of this equation. So the integral of 1 with respect to x squared y is just x squared y, and the integral of cosine x is just sine x, and we can put the arbitrary constant of both of those integrations on the right-hand side. So that is at least the implicit solution to the inhomogeneous differential equation that we proposed, right? But we were just lucky that the left-hand side was in the form of a product rule that was easily identifiable. So here is the natural question that we want to answer. Can we do this for all first order linear, inhomogeneous, because we already know how to solve homogeneous, inhomogeneous ordinary differential equations? You can probably guess that the answer is yes, but let's see if we can figure it out in a clever way, in particular a formal way. So the general form of this equation is going to be equal to y prime plus axy is equal to bx. And we're going to assume that bx is not equal to 0 because we've already considered the equal to 0 case. So does there always exist? So we're going to be looking for some function f of x such that f of x y prime plus f prime x, let's actually write it as f of x ax y is equal to fx bx. So you may be thinking like, okay, well, what's going on here? So all I'm really doing is just multiplying both sides of this equation by f. And of course, you can multiply both sides of the equation by any function f. But is there something special about this function f? Well, what we want is that this to be equal, at least equality in terms of the equation, as the derivative of f of x times y is equal to fx bx. That is, we want to multiply both sides of this equation by some function f such that the derivative of this via the product rule gives us precisely that. Because if so, if such a function exists, then what we have is the differential of f of x times y is going to be equal to f of x b of x d of x, and then we can integrate both sides of that equation, and then we have y times f of x is equal to the antiderivative of f of x bx dx, which is the implicit solution of the differential equation. Because notice the right-hand side does not have y in it, so it's not an integral equation. And we just can divide both sides by f of x, and we have y is equal to something that doesn't have any derivatives in it at all. So that is the implicit solution to that differential equation, if such a function f exists. So now, if we can find such a function for all particular equations, then we're practically done, right? So let us see if we can formulate exactly what type of structure this f has and what it actually depends on. So what do we want? So we want f of x y prime plus f of x ax y equals f of x bx. We want this to be equal to the derivative of f of x times y. So let us look at precisely of what that actually should be. So the left-hand side would be f of x y prime plus fx ax y, and we want that to be equal to the first times the derivative of the second plus the second times the derivative of the first, right? So this is there, and this remains. So if you notice, we have something in common with the left and the right. We have an fxy prime, which is actually pretty nice. And then what are we left with? So we're left with f of x, a of x, y is equal to y f prime of x. So let's assume that y is not identically equal to the 0 function, which is going to allow us to divide both sides of this equation by y, and that's going to give us a very basic looking equation, in particular f of x times a of x is equal to f prime of x. So what is this? Well, this is an ODE in terms of the unknown function f, right? So our goal is to solve this differential equation in f. So we have to solve a differential equation in order to solve another differential equation. But there's something interesting about this equation because we can write this instead as the derivative of f with respect to x is equal to f times a of x. I'm just writing f as just f of x just to make things nice. And notice that this is the same as the derivative of f over f is equal to a of x times d of x, and we should notice that this is precisely a separable equation. So we have over here the natural log of this function f is going to be equal to the integral of ax dx. So what do we have in terms of the solution to this differential equation? So that means this function that we seek that makes this beautiful backwards product rule work is precisely equal to e to the integral of ax dx. Some people will call this an integrating factor or an integration factor, right? Where ax is the a in this expression, y prime plus axy is equal to bx. So it doesn't really matter what bx, the integrating factor for this differential equation, this inhomogeneous differential equation, is going to depend on a and a only, which is actually pretty nice. Now, you may be wondering, okay, well, what about the c that's actually going to come out from that integration? You can actually choose any constant c. So you can choose any constant c. So in particular, what we usually do is we choose c to be equal to 0. So for example, if ax is equal to cosine of x, then f of x would just be e to the sine x. We wouldn't put a plus c or a plus 5 or a plus pi or anything like that. So that's particularly the 0 constant antiderivative, and that would be your integrating factor. Now that we know theoretically that this f exists, and since that f exists, the previous theory holds, let's work through a couple numerical examples on how to solve inhomogeneous first-order linear ordinary differential equations. Let's look at this first example to sort of get an idea of how to work through an inhomogeneous first-order linear ODE. So what we have here is y prime plus y is equal to 1 divided by 1 plus e to the power of 2x, with the initial condition that y of 0 must be equal to 2. All right, so how are we going to approach this? So classification of the differential equation obviously is a good place to start. We have a function of x on the right-hand side. We have the first order ODE. It's a linear ODE. We don't have y prime squared. We don't have y squared. And also we don't have any function in front of y also, which is actually pretty nice. So it looks like a very friendly ODE, at least theoretically. So if we want to start giving things some names, what we have here is y prime plus ay is equal to b. In particular, a of x is equal to 1 in this case because there is no function of x in front of that y. So if we want to look for an integrating factor to make this into a backwards product rule, the only thing we need to focus on is that function a. So the magic integrating factor f of x is going to be equal to e to the integral of ax dx as long as your equation is placed in this form. So for our particular equation, we're going to have e to the integral of 1 dx, which is just going to be equal to e to the power of x. So if we multiply both sides of this equation by e to the x, then we should have a backwards product rule set up for us right in front of us. So let's see if that actually is the case. So on the left-hand side, that's going to give us e to the x y prime plus e to the xy is equal to e to the x divided by 1 plus e to the 2x. So if you look at what we have here on the left-hand side, we have the first derivative of second plus the second derivative of the first, because the derivative of e to the x is itself. So this is indeed a backwards product rule on the left-hand side. So on the left-hand side, we have the derivative of e to the x times y. And on the right-hand side, we have e to the x over 1 plus e to the x, the quantity squared. So once we start integrating this right-hand side, because we're going to be shifting that dx over there, and then we're going to be integrating this expression, I'm going to be using a u substitution for that right-hand side. So I'm going to be letting u be equal to e to the x, implying that just du is equal to e to the x dx, which means that du divided by e to the x is going to be equal to our differential of x. So once I have that, well, the integral of d exy is just going to be equal to our exy. And on the right-hand side, we're going to have the integral of e to the x all over 1 plus u squared times du divided by e to the x. So once we have our e to the x there, we see that they nicely simplify. So what are we left with? We're going to be left with e to the x times y is equal to the integral of du over 1 plus u squared, which we should know as the arctangent of u plus some arbitrary constant c. So we can solve this equation very nicely, and don't forget u was just a fancy way of saying e to the x. So we're going to have y is equal to e to the minus x times the arctangent of u plus c. Right? So that is our general solution. So now what we need to do is we need to figure out our particular solutions to our differential equation. So keep in mind our initial condition was that y0 was equal to 2. So once we replace this into our general solution, what we're going to have is we're going to have 2 is equal to e to the 0, which is equal to 1, times the arctangent of e to the 0, which is 1, plus c. The arctangent of 1 is going to be equal to pi over 4. So we're going to have that c is equal to 2 minus pi over 4 as our particular constant. So therefore our particular solution, or y particular, is going to be equal to e to the minus x times, let's write this as 2 minus pi over 4 plus the arctangent of e to the x. Right? So that is the particular solution to that inhomogeneous differential equation. So let's look at another example that is a little bit more fun, let's say. That is also a linear first order inhomogeneous differential equation. So example 2. Let's assume we have 1 plus x squared dy is equal to, not equals, let's do plus 2xy dx is equal to the cotangent of x dx with the initial condition that y pi over 2 is equal to 2. Alright, so the first thing that we need to do is write this in our typical form. So what I want to do is I want to divide everything by dx. That's going to give us our dy dx in the first term. And then I want to divide everything by 1 plus x squared. That's going to get our dy over dx term by itself. So once we have that, we're going to have y prime plus 2x over 1 plus x squared times y is equal to the cotangent of 1 plus x squared on the right-hand side. So this is a first order linear inhomogeneous ordinary differential equation. So our special function that we seek is going to be equal to e to the integral of this function here, which is 2x over 1 plus x squared dx. You should be able to identify that as just a chain rule problem because that's just the derivative of the natural log of 1 plus x squared. You could use a u substitution to verify that if you're not comfortable, which is equal to just 1 plus x squared, which means if we multiply both sides of this equation by x, 1 plus x squared, it's actually going to put us back where we started. So we're going to have this equation, 1 plus x squared times y prime, plus 2x times y is equal to the cotangent of x. And that's okay. You know, we just were being safe, right? And if you sort of notice here, what exactly do we have in front of us? Is this really backwards product rule? So what we have here, the derivative of y is y prime. The derivative of 1 plus x squared is 2x. So it checks out. So the left-hand side is precisely the derivative of y times 1 plus x squared. And on the right-hand side, we have the cotangent of x. So once we integrate both sides, what we're going to have is the differential of y, 1 plus x squared, is equal to cotangent of x times the differential of x, and then we're going to be integrating both sides of that expression. So what we're going to have is we're going to have y times 1 plus x squared, and the antiderivative of cotangent is going to be the natural log of the absolute value of sine plus some arbitrary constant c. Right? So once we have this, then we can actually go ahead and find our constant c, because we know that y of pi over 2 must be equal to 2, and we can find it here and just keep this as an implicit solution since we're going to have a bunch of nasty fractions going on. So y must be equal to 2, and then we're going to have 1 plus pi over 2 squared, so that's going to be pi squared divided by 4, is going to be equal to the natural log of the absolute value of sine pi over 2. So what is pi over 2? So pi over 2 is going to be 90 degrees, so that's going to be the natural log of 1, right? So the absolute value of 1 plus c, but the natural log of 1 is 0, so the right-hand side is just equal to c. So what we have here is c is equal to 2 plus pi squared over 2. So that is our particular solution, or our particular constant. So therefore, our particular solution, yp times 1 plus x squared, must be equal to the natural log of the absolute value of sine x plus 2 plus pi squared over 2 as our constant. And that is our implicit particular solution. You can divide both sides by 1 plus x squared if you really want to. Obviously, x cannot be equal to plus or minus I, but I don't think that should be an issue here. So this is actually how you solve first order linear and homogeneous differential equations, and that actually gives you a wide class of differential equations, but there are infinitely many other classes that are far more difficult, and we'll get to each of them case by case. So I hope you enjoyed this video, and I'll see you in the next one. Take care.